There we go. A round of applause for that man. Oh, this is suddenly much louder than I was expecting. I'll speak very softly. Okay, so the goal of software development then is minimizing lead time to business impact. It turns out that the minimizing lead time to business impact isn't that hard. Okay, you can minimize lead time to business impact mostly by shouting at people. That works. You can beat them. I mean, I wouldn't suggest beating them, but you can put people under insane amounts of pressure, and that will allow you to minimize lead time to business impact once. Okay? Unlikely to happen more than once, certainly unlikely to happen more than twice. Okay? Because either all those people are just exhausted now, or they've quit, or you've been arrested, or something's happened. Okay? So that's not the hardest thing. The hardest thing is sustainably minimizing lead time to business impact. And that is the goal of the system of work that we call software development. We want to be able to create business impact at will, in a very short amount of time, sustainably. Okay? And once you start thinking in these terms, a number of things become apparent. So the first thing that becomes apparent is this. The goal is not producing software. We call ourselves software engineers, and that's like a plumber calling themselves a pipe engineer, right? The purpose of plumbing isn't pipes. The purpose of plumbing is heating and water, okay? The purpose of what we do is information. We used to call it information technology, applying technology to information, but that wasn't cool enough, so now we're software engineers. And some of us are software craftsmen, which I think is kind of cute. Well, I'm not a fan of those kind of terms because software isn't the point. Okay, business impact is the point. So produce is an interesting word. It's a Latin word from prodere, which means to make things. And we see it a number of places. We see the word, what's the word? Versions of this word in different places. So production is the same root as produce. And productive. So all of these are from the root prodere, okay? And what that suggests is building things. So if I'm making widgets in a factory, I'm producing things, right? That's productive. And if I produce more widgets in a given amount of time, or produce more cars on a production line, there's that word again, right? Then that's better, okay? So the idea is that I want to make more widgets, but we don't want to make more software. We want to make business impact. And we want to make business impact quickly. And quickly suggests less software. And so we have this kind of this awkward conflict, which is that productive is not the same thing as effective, which is a shame, because for decades we've been talking about software productivity metrics and measuring productivity and talking about measuring productivity, and it's the wrong thing. Okay, we shouldn't be looking at measuring productivity. And the problem is this: code is not the asset. We think of code as an asset. We use languages like, legacy, even legacy code. We go, oh, legacy, that's a legacy system. Legacy is a thing of value you leave to the next generation. That's your legacy. Okay? So we think of software as valuable. We talk about technical debt because good software is an asset, bad software is debt, right? So we think of code as an asset. Code isn't an asset. Okay? This is the uncomfortable truth. Code is not an asset. Code is cost. Okay? Code is the cost of getting the business impact. The business impact is the thing we care about. Okay? And there's lots and lots of types of cost. Code has cost in lots of different ways. There's the basic writing cost, the cost of having human beings, ideally highly paid human beings. Hopefully you're all highly paid human beings, right? Highly paid human beings writing code. So I've got 10 people in my team. Every single day, that's 10 people days of cost. Okay? So conservative estimate, about $1,000 a day. Fully loaded cost for a human being. So that's about $10,000 a day. That's $50,000 a week. There you go. Is just my cost to start writing stuff. So that's the obvious visible cost. Then there's a bunch of other costs. Waiting for code costs. This is called cost of delay. Okay? So cost of delay is this, say I have a need, and the need is I need some information, and given that information, I can make good decisions. There's a buying decision I have to make every day. I have to buy certain things every day. And if I have that information, I can know exactly how much of the thing to buy. If I don't have that information, I have to guess. And every day I guess either slightly high or slightly low because I'm guessing. And that costs me 5,000 euros a day. Okay? So every single day I don't have a solution to that problem. 5,000, 10,000, 15,000. And so but this is a hidden cost. We don't see the cost of not having the thing. Okay? And this cost of delay is huge. It dwarfs the cost of building things. And when I have several things, several needs that are unmet, all of those things going on at the time, the cost of delay for all of those things starts to balloon. Okay? So waiting for code costs, changing code costs, going in and maintaining code costs. And there's probably the single biggest cost within changing code is figuring out what the hell it does, right? Understanding code costs. Understanding code that you didn't write. Sometimes for me, understanding code I did write. But 6 months ago me, and 6 months ago me is an idiot, right? I'm super smart now. 6 months ago I was an idiot. Of course, in 6 months' time, I'll be saying that 6 months ago me was an idiot. Because 6 months ago me, it turns out, is always an idiot, which is slightly frustrating. I mean, it either means that I'm learning or I'm not learning. One of those is true. But essentially, so code is cost. So let's think about understanding code then. What does it mean to understand code? There's three kinds of, you can imagine sort of three kinds of code, if you like. There's code I know, because I wrote it, okay? So I'm pretty confident about that. I wrote it recently enough that it's still there. And then there's code that's been around, that's stable, that everyone knows. It's well documented, all of that stuff. So those two, I'm happy working with code like that. I'm happy working with well documented, well established code. I'm happy working with code that's new enough that I wrote it. Then there's that awkward code that's kind of code no one knows. So it's been around long enough that it got old, right? But no one noticed it getting old. We didn't do anything deliberately about it getting old. It just got older. And maybe the people who wrote it maybe rotated off the team, or maybe they forgot what it did, or maybe they couldn't remember the exact reasons why it did it, or maybe the reasons are changing anyway. Maybe it's being used for something it wasn't supposed to be used for. But no one really knows. And if you look at a sort of volume graph, if you like, a histogram of that code, you tend to find that a huge chunk of code fits in that middle gap. Okay? It's code that's old enough that no one exactly remembers it, but not really cared for, not really nurtured. And so my premise then is this. Code should be stabilized or killed off. That's it. Okay? Code should be stabilized or killed off fast. Okay? And if we can get into the habit of either stabilizing code or killing code, then it means we only end up with code that we wrote recently or code that's really stable and well known. It sounds really obvious. It's really hard to do deliberately because entropy, right? Because the default state is that stuff just gets older. Okay, I have some disappointing news. At the end of this talk, everyone in this room will be 50 minutes older. Sorry, can't do anything about that, right? Here's the thing. All of the code that you left back at work, that's 50 minutes older too. Yeah, and tomorrow, guess how much older it'll be? Yeah? So code is aging all the time. So one of the things I was doing after I left ThoughtWorks and went off into this trading firm is collecting patterns of behavior and patterns of software that I felt were enabling these high-performing teams to do really, really astounding things. And I spent 8 years at ThoughtWorks, had a fantastic time there, and I thought I understood all this software delivery stuff and Agile and all that, and so then I went into this, I come to conferences and talk about it. And then I went into this, to join this very small team, and I'll talk a bit more about them this afternoon. But I joined this very small team, and they were doing some really, really unusual things. And they were the most agile group of people I've ever worked with, and they were breaking all the agile rules. Okay? Ironic. Maybe not. But so here's a couple of patterns then. And again, as I said, I'm going to talk about some more later on today. But here's a couple of patterns that I've sort of derived, if you like, that I observed from this team, and that I've seen elsewhere and that I've applied elsewhere that help me reason about stabilizing or killing off code. Okay. So a couple of complementary patterns. One is called a short software half-life, and the other is fits in my head. So I like naming things, okay? So short software half-life fits in my head. So let's take a look at the first one then. Short software half-life. So half-life of software is it's a theoretical idea. It's a mental model. So the half-life in physics is essentially this. If I have 1 million atoms of a radioactive isotope, depending on what type of element it is, I can know exactly how long it will take for half of those atoms to decay to a more stable state. That's called its half-life. Okay? So for each different type of element, there's a different half-life, and I can measure it, and I can know it precisely. It's a measurable thing. What I don't know is which atoms. So I can look at these things, 1 million atoms, and half of them are going to decay in a certain amount of time. Okay? So if I only have a single atom, then what happens is after that half-life, it's either decayed or it hasn't decayed, and in fact it's in this weird state where it's both of those things until I look at it. And if you put that in a box with a cat, you get a really pissed off cat, and that's most of physics. Okay? So you now all have a physics degree. Okay? You can print them online, it's fantastic. So I applied this idea to not putting code in a box with a cat, because that's silly, but the idea of a half-life to software. And I'm thinking about this. How long, and here's a thought experiment to try now. Think of the code you're currently working on, or that you're currently responsible for, and think, how long would you need to go away for so that when you came back, half the code has changed? Half the code has either been changed beyond recognition, you wouldn't recognize it again, it's been deleted, it's been rewritten, it's been changed. Half of it hasn't, but half of it is completely different. How long would you need to go away for? Okay, and I asked this question in my class called Software Faster, and I asked this question in my class, and one of the first times I ran this class was in Scandinavia, and someone was working for a Swedish bank. That morning on his way to the class, he had been working with some software that was written in 1967. Right? He says he reckons the half-life of that software is millennia. He's fairly confident his grandchildren will be working on that system. Okay, so am I. Right, and if we think about half-life of software, it's typically, I don't know, years. Right, years, maybe decades. And so I did a back-of-an-envelope calculation with the code we were working with this trading systems. And these are non-trivial systems. And what was happening was the code was just changing under my feet roughly every 6 weeks. I reckon the half-life of the code was about 6 weeks, about half of it was different. And it was a crazy, crazy, crazy rate of change. But what was happening is these guys were fearlessly deleting code, okay, and rewriting code, because their premise was, I now know more, and I can get from public static void main to something that I want faster than I can understand this code, manipulate it, change it, make it do what I want. And also, the next time I write it, it won't have any of the speculative things that I put in that I didn't end up using, okay? So let's think there's some design considerations that are going to enable us to do this. So we can't just do that with code. You can't take a huge, big monolith of tightly coupled code and confidently start deleting half of it. Okay? That's not going to fly. You're going to get in all kinds of trouble there. So I'm going to need some discrete components. I'm going to need to build small, separate pieces. Okay? Because if I have a discrete component, I can reason at a component scale. And I want to define a component boundary. I want to define what happens at the edges. Because then if I can think about what happens at the edges, I now own the center. And I want to define a component purpose. What does that mean? That means, what is the point of this software? And I know a lot of people are kind of, we're not fans of documenting code. Code should be self-documenting. Code self-documents what it does. Well-written, cleanly written code tells you what it does. It doesn't tell you why it's there. Okay? It doesn't tell you its purpose. It tells you what it does. And the other thing that it doesn't tell you is what isn't there. It doesn't tell you all of the design considerations, all of the other ways of doing this that I thought through and I thought, I don't need those. Yeah, I'll leave those. I'll do it this other way. It doesn't show you the 3 or 4 iterations it took to get there. I mean, I can pore over version control history if I want to, but when I'm looking at code, the code is telling me, and it's kind of obvious when you say it out loud, the code is telling me what it is. It's not telling me what it isn't, and it certainly isn't telling me why it is. Okay? So if I don't have somewhere vividly captured the purpose of that component, I can't reason about it. Or at least I can try to infer it by looking at the code. I wonder why this is here. Oh, look, it seems to do this. That must be an important thing, therefore. So I just derived the purpose of that. It may not be. The purpose of it may be to do something else, but when you stand back and squint, it looks like it does a different thing. Okay. And finally, I want to define its responsibility. Responsibility, slightly different from purpose. So the purpose is why it's there. Responsibility is what it owns, and again, going back to the boundary, therefore what it doesn't own. So again, if I'm going to replace it, if I'm going to change it to be something else, I need to know what it's there, what it is, why it's there, what it's responsible for. Okay. Once I understand those things, I can start to reason about it. Then also there's a life cycle element to this. So components have a life cycle in terms of like I dreamt them up, I decided I needed them, I started writing them, I introduced them, and so now I need to kind of think about how I'm going to look after them. So in terms of stewardship then, I need to write tests and documentation around these things. Okay. When we do the specification by example, or programming by example, or TDD, or whatever you want to call those things aren't tests. You're not writing tests, okay? Sorry, programmers, those things aren't tests. They're executable specification. You can use them to verify some of the behavior of your application. That's great. That's a side effect, okay? You haven't got tests for your code yet. Don't kid yourselves. And again, documentation. Tell me why something's there. Tell me the decisions that we made. Mike Nygaard has a lovely blog post that you can find on the Googles about architecture decision records, ADRs. And what he does, essentially, it's just a really simple markdown, basically a blog post. And in the blog post, he says, here's the decision we made, here's the people who made it, here's the things we considered, here's the things we discarded, the choices we decided not to do, and so this is what we ended up with. And for extra credit, here's some of the risks that it introduces. This is the problem it solves, but also here's some of the baggage it brings in. And that stays in version control. So I can look at the decisions that we made over time. And so someone new comes into the project and they say, oh, hey, you're doing this all wrong, and you should be using JSON and MongoDB and whatever else. And we go, okay, thanks for your valuable input. So here's when we made that decision. Here's how we made that decision. If something has substantively changed since we made that decision, then let's have the conversation. And they go and they read it and they go, oh, and then, oh, wait a minute. Oh, you thought about all that. And you thought about that. And you thought about a thing I didn't think about. And you ended up with, okay, I'm good with that. It's surprisingly effective. Yeah. But also, it's there to be challenged. Well, do you know what? This has changed since then. So let's try an experiment. Okay, let's try an experiment. Fantastic. Let's do that. So if we have component test documentation, if we keep a journal over time of the decisions we make, which is different from a wiki. A wiki is current state. In a lot of places, a wiki is just a hipster version of SharePoint, right? It's where information goes to die. But we used to put information in Word documents to go and die. Now we put it in HTML pages to go and die. So this is a blog, and the blog is searchable, and it's easy to find things. And I want to optimize for replaceability. So that means I'm typically going to not introduce libraries that couple components together. Because if I introduce libraries that couple components together, then bad things can happen, right? What it means is, okay, I'm reducing duplication, which is good, but now I'm introducing coupling, okay, which is not great. So if I optimize for replaceability, I might make different decisions. And I should expect to spend time investing in stabilizing. Right? I should expect to spend time, if this component is going to be long-lived and is going to be something that someone wants to come along and replace, and that someone might be me, then having some documentation, having some tests around it, bothering to invest in it becomes useful. Here's another thing. If all my code is changing on a frequent basis, the information, the knowledge about what that code does is in the team, right? So that means I want to invest in building a stable team. That does not mean invest in building a static team. Static and stable aren't the same thing. So a static team never changes, okay? The static teams get stale and old, and they lose their sense of breadth, if you like. They become very kind of echo chambery. A stable team means I'm very deliberate about onboarding and very deliberate about exiting. Okay? So when someone new joins the team, there's a whole process where we bring that new person up to speed. When someone leaves the team, it's sad. It's a sad thing, but we make it a thing. right? And we make sure, particularly, that if they have any knowledge that no one else has, that we try and capture that knowledge, ideally before they leave, right? So it's not a kind of, oh, you're leaving in 2 weeks, write down everything you know. It's that over time we have invested in creating that shared understanding. So stable teams can move quickly, okay? Stable teams, there's a lovely African proverb. If you want to go fast, travel alone. If you want to go far, travel together. I added a little addendum. If you want to go far quickly, pack light. Okay? It's not a binary choice, it's a scale. It's a scale from being completely alone to having a huge army of people and loads of stuff. You can be somewhere on that scale. You can have a small bunch of people. So that's my short software half-life. Then, so my other pattern then is fits in my head. So fits in my head, this is based on a chap called James Lewis. So James Lewis, a number of things. Well, he coined the term microservices, or is one of the people who coined the term microservices. So it's basically all James's fault. But no, I work with James at ThoughtWorks, and he has my favorite complexity metric. Okay, so he says he doesn't like to look at code that's bigger than his head. So his head is about that big. That's about a 24-inch monitor. Okay, so that's about the size of James's head. So James Lewis's head, I'm proposing, should become an SI unit, which means we need to chop his head off and put it in a fridge in Paris. Okay, but until we can do that, he seems resistant to this. I don't understand it. But until we can do this, then well, you have to imagine James's head, but it's about a screen of code, right? So if there's code, and of course, you can muck around with font size as well, but let's make it legible. So if it's more than if he has to page up and down to look at something, it's probably too complicated. Okay, so a function or a method or whatever else it might be, there's too much stuff there. And so he says, okay, that means he needs to make it smaller, simpler, so it will fit in his head. So fits in my head then. Obviously, it's a metaphor, right? You don't actually need James Lewis's head, nor do you need a 24-inch monitor. It's about whether you can reason about something. And there's some fairly obvious logic here. You can only reason about something that fits in your head, right? That makes sense. But then the converse of that says this. If you can't fit something in your head, you can't reason about it. And so what we do instead is we have coping mechanisms. So one of our coping mechanisms is we divide and conquer. So it's the way we do analysis, right? So analysis, the way I make a big complex domain fit in my head is I look at a small part of it. So if someone says, go solve healthcare, that's a huge problem. And so go solve patient record management, that's a big problem. Go and think about a patient visiting a hospital, visiting a doctor at a hospital, and think about what that would look like. Oh, okay, yeah, I think I can fit that in my head. So now I can start to reason about that. So, but what we do with big, ugly software systems is rather than simplifying them, because that's time and effort and hard, is we come up with techniques for actively ignoring parts of it. So TDD is a fantastic way of actively ignoring stuff that's going on around you. Yeah? Or in fact, let me qualify that. Mocking and stubbing is a fantastic way of actively ignoring things happening around you. So where you're writing your tests and they have lots and lots of stubs and mocks, what that should be telling you is, in order to reason about this piece, I have to ignore loads and loads of other stuff, which suggests that it's coupled to loads and loads of other stuff, which is bad. So you can think of mocks as basically painkillers, right? They're your drugs. So the more things I can... mocking's easy. I've got mocking frameworks that make it easy. Here you go. It has free access to drugs, so you don't have to think about painkillers, so you don't have to think about the pain of the complexity of this system. Well, we should think about the complexity of the system. I want to take all the mocks away from all the people. And they go, oh, no, look, I can't test this thing. Right, so now let's break the system up so that you can. But fits in my head occurs along multiple dimensions. It occurs along the dimension of technology. So I want technologies that fit in my head. Some languages fit in your head better than other languages. Two of my favorite examples, Clojure and Scala. Right? So Clojure is a Lisp. It's basically two parentheses. That's most of Scala. That right there. There you go. It's a little international sign language for Scala. Okay? For Clojure. So Clojure is a very, very simple language. There's not much to it. It's lists. And it's called homoiconic, which means that a Clojure program is written as a Clojure data structure, right? So Lisp is, so you have lists, and the program itself is a list, so you can manipulate code as code. It's as code as data. It's fantastic. And there's typically one way to do something. in Clojure, and it's typically fairly obvious how you do that. And if it's not, you look in some of the core libraries and documentations and tutorials, and there's a very obvious style. Scala, least opinionated language I've ever met. Scala doesn't care. Okay, so reusing code. So if I want to reuse code, I say, let's have class-based inheritance. Yep, you can have that. What about mix-ins? Yep, we can have mix-ins. Closures over functions? Yeah, sure. Do what you like. Okay, thanks. What about something as simple as looping, right? Going through a sequence. Well, yeah, we've got a for loop. Yeah, we've got an iterator. You've got recursion. You've got functional like map reduce type. Yeah, sure. Any of the above. Oh. Because what that means is this. As soon as I have 5 programmers, I have 8 dialects of Scala. Yeah? And so that means now, which is great, it's a great language for trying all kinds of crazy stuff out, just not in my code base. Right? And so what that means is you as a team need to be a lot more opinionated about those things. So we need to say, this is our local style. It happens at multiple scales. So I want to be able to look at any code, and that code fits in my head. So if we have a consistent style of code, I can look at anyone's code, and I don't need to think, oh, this is Bob's dialect of code, so I just need to switch into Bob mode. Okay? Although there's some interesting psychology that suggests that once you do, if you have a really high-performing team and everyone knows how everyone else works, when you see someone else's dialect of code, they have a different style of bug. Right? Different people introduce different kinds of bugs. They misread things differently. And so I know if I'm looking at Bob's style of code, it's probably going to, yeah, there it is, right, I'll just fix that. Right? But let's not do that. So what we want is consistency. Okay? So across multiple scales. So I want to be able to look at any class and it looks like I wrote it, or it looks like anyone in the team wrote it. And I pan back and I look at a component, and that component fits in my head. And I can look at the way that a bunch of different components talk to each other, and they all, sorry, my phone's just started ringing. I look at a bunch of different components talking to each other, and they all talk to each other in a consistent way. So that fits in my head. I can reason about a system. And if it's done, if we build something consistently, something I learn over here, I can apply over here. And that reduces my cognitive load. It makes it easier for me to reason about things. When we start getting slightly larger, we start scaling, what happens is you have a bunch of different teams, and all the agile stuff tells you that the team is the unit of delivery, and teams are autonomous, and teams should make their own decisions. And in systems theory terms, we call that local optimization. And local optimization is fatal for any kind of global delivery. Okay? Any kind of global optimization of a system will be sabotaged by local optimization. And one of my favorite examples of local optimization is when you see the slide that goes up that says, these are some of the technologies we use. We're using Mongo and Cassandra and HBase and and there's 15 different things up there. And they're going, look at us, we're this cool. And I'm like, you're not the operations team, are you? You're not downstream of all of those crazy decisions, are you? You're not the person installing, upgrading, securing, monitoring, administering, are you? No, of course not, because otherwise you'd probably be making that much, much, much smaller set of sensible choices. Okay, and so there's a couple of ways we can do this. One is I can say, right, so James again. James has to be in all the meetings. That's a good way to get consistency. That'll work. Well, yeah, except that A, it sucks to be James, and B, that means that James is now a massive bottleneck. Okay, so that's a problem. So instead, what we could do is this: is we could all wear a little badge that says, "What would James do?" And we're in a meeting, and we say, "Okay, we need to make this decision about, persistence or about monitoring or whatever it is. What would James do?" And that means that we're like, not actually James, but what you've done is you've created some shared values, some shared guidelines, so you can all make consistent decisions. And the thing to do then is to check in with each other. We decided this thing. We're thinking about doing this thing. What do you guys think? Well, that makes sense because we're doing this thing, and that's kind of aligned. Or, well, we're doing a different thing over here. Let's have a conversation about that and figure out what the most sensible thing to do is. And then you can start to scale. Contextual consistency then. So we want to agree these guiding principles, agree idioms, agree how we're going to do things around here. And at that point, difference is data. So that means if I see something that's not like the other things, that's probably signal that something interesting is going on here. Okay? And in particular, the idea that familiarity is not the same as simplicity. So what does that mean? That means things that I'm used to seeing, that doesn't necessarily make them good ideas, it just makes them ideas that I've seen a bunch of times. Okay? So we get the boiling frog syndrome. So you put a frog in cold water and you gradually heat the water and the frog boils to death. You know that's not true. If you heat up a bowl of water with a frog in it, the frog goes, wow, it's getting a bit warm in here, and jumps out. Okay? However, we all think it's true because we've all heard the story. And that is boiling frog syndrome. So it's a little bit meta for you. Okay? We all think a thing that we heard is true. So I need to move on because I'm running out of time and I'm not, well, actually, no, this is going quite well. I thought I had a ton more stuff to get in, and I've just landed on the bit that I want to tell you about. Microservices. There we go. So, oh yes, I'm not calling them microservices. I'm calling it a replaceable component architecture. And this is what I mean by an architectural style, okay? Any architectural style which has components which are replaceable, okay, this creates options for me. It means I can reason about code differently, okay? There are many, many replaceable component architectures. So what does a replaceable component architecture mean? It means I start with this is how I achieve my sustainably. Okay, this is how I start building my sustainably reducing lead time. Okay, if I keep things replaceable and I keep things componentized, it means I can reason about them. So there's my component. There you go. Took me ages to draw that. Okay, here's another one. Okay, so this is my component diagram. Oh, there you go. Let's have some more. Right. So these are components. Okay, each component does a thing. But remember, each component has a hard shell. Okay, it's wrapped in a hard shell. And these components, they talk to each other, they send messages to each other. Okay? So they're like little computers passing messages. Okay? I'm not the first person to use the phrase little computers passing messages. Does anyone know who was the person who said little computers passing messages? No one. Alan Kay says one person. Well done. So this is the man who coined the term object-oriented programming. And he said, object-oriented programming, he said, objects are little computers passing messages. And he recently, a few years ago on a mail list, he said, my biggest regret with OO is I didn't call it message-oriented programming because the objects were a complete red herring. He said, really, it's all about passing messages. We, as an industry, massively messed up OO. Okay, and I still hear people who I regard as fantastic software people talking about OO, and they still talk about, these objects, so we model the objects in our world, and those are the objects in our... No, they're not. No, they're not. An object-oriented system doesn't model objects in your world. That's not what objects are. Objects are little computers. They're things that do stuff. So the objects in your world are called entities. They've always been called entities. They're called entities in relational model. They're called entities in databases. They're called entities in object-oriented. They're called entities in domain modeling, right? In domain-driven design. They're entities. They're things. They have state, and they have identity, okay? So an object in OO does things with entities, and pretty much anything interesting requires using multiple entities. So for instance, if I'm moving money between accounts, I'd have an object that does that. I'd have a money transfer object. So really the things we think of as services, verbs, verb phrases, those things are objects. They're little computers. And what they do is little computers pass messages to each other. Okay? So he was talking figuratively. This is back in the 80s. Yeah? We now literally have little computers passing messages. You saw some. There was a little pile of little computers here, right? If you're in the Kubernetes session. Okay, literally little computers. He couldn't have imagined that. Or maybe he did, right? But we've got literally little computers passing messages. That's way cool. Okay. So Alan Kay says this, and and so now I can reason about a component purely by thinking about it in terms of the messages it produces and consumes, right? And so that means I can test a component purely in terms of the messages it produces and consumes, which is kind of cool. Because that means that now unit testing, functional testing, integration testing, all of those kinds of testing all collapse into the same space, which is testing. Okay? And replacing one of those components, I replace the green bit, I replace the innards, I leave the hard shell. So the API defines exactly my contract with the world. And again, that's kind of useful. So microservices can be a replaceable component architecture. They're not necessarily. And a lot of the places I see them, they're not. Okay. My beef with the term microservices is this, is microservices suggests smaller is better. Microservice, I've got this one-line service, right? So you look at the proliferation of tiny little JavaScript libraries. And there was that wonderful thing recently where someone removed a JavaScript library that pads spaces onto the left side of a string. Apparently, these days, we need a library to add spaces to the left side of a string. Right? Oh, my word. Because it's far more complicated to write some code to figure out how many spaces I need to add than to add a dependency management tool, download the dependency, pull down the internet that the dependency depends on, and then realize that that dependency package requires another dependency package to function as a dependency installer. Why not just add the stupid spaces, right? But so we can go too far with the micro. So microservices can be a replaceable component architecture if I choose to optimize for replaceability and consistency. If those are the things that I care about, if those are the things I value, I can get to a replaceable component architecture. It means that I can reason about each of these microservices. What does it do? What's its responsibility? What's its boundary? What's its purpose? Once I understand the purpose of that thing, I could replace it with a different thing. And I know that I can do that confidently. And once we can start doing that, that creates options for changeability. That creates options for agility. Okay? Smaller isn't necessarily better. We don't want littler services. We want replaceabler services. So more replaceable. Unfortunately, replaceabler isn't a word. I'd like it to be a word. More replaceable is better. Okay. So my message to you then, my plea to you, my request to you is this: kill code fearlessly. Okay? So remember, we've got the code I know, we've got the code everyone knows, and we've got the code no one knows. Yeah? So if we can confidently kill that code, that means we're in a position where we can move quickly, right? Where we can iterate quickly, where we can respond to business need quickly, which is business agility. Okay? Remember, we're trying to minimize lead time to business impact. So that's all I had. Thank you.